better?
Yep.
Okay. So I work for Genetech. I actually don't have a team anymore. So I'm working as technology architect, which is not a title that really means anything. I do some technology oversight, some technology intelligence, some training, basically setting the direction that we go with. As we said before, we have a pretty large organization and growing steadily. So the problems don't go away by themselves. So we're headquartered in Montreal, but we have development offices in Paris. We have some people in Pennsylvania. We have a few other offices around Quebec, the province. So what we do has nothing to do with genetics, despite the name. So we mostly build software to manage very large-scale security operations. So by large public and critical infrastructure, we mean things like electricity, like airports, large airports, Target as a whole. They're big, like all the cameras and all the Target systems in the country. In the US, for instance, this is like we manage those kinds of things. So we're mostly a C# shop. We're C++ initially, then moved on to C#. But so since I joined about 8 years ago, my target was to build a whole new project in F#, which ended up being a really massive embedded application. Running on Windows, but still embedded, as embedded as things are in 2018. So this has been going on. We also have a few new appliance projects which are written in Erlang, so we're also for that. So first, critical lesson. There is one critical lesson that is not technical, that is name your projects. Do not leave your project with a generic name and then hand them off to someone. And so we'll just name it anything. So this is a DSL, and you know my name. Can someone guess with the DSL what the project was named when I handed it off to someone?
Vincent DSL?
Close. It was called Vin Diesel.
Vin Diesel.
And then things like that started popping up. And then around the office, people would be like, oh, I convert that to Vin Diesel. And every time, like, damn it. And you obviously can't, there's no name that will get over this. So this was my, I deserved this, but it was a bit ridiculous. So I've read timeline spec, which is the title of the talk. So what's the domain here? So domain-specific language implies a domain. So the initial case, generally it's writing integration and system tests for distributed systems. So there's multiple systems doing things and being acted upon, and it's kind of hard to test those things sometimes. So what happened is that around 2015, I was getting my hands back in the code, around from drawing boxes and arrows as an architect. And I had to write tests for it. And then I started writing it, and it was terrible. It was just like the experience of, not like the testing frameworks, but just like of writing tests. Those kinds of tests was really hard, really error prone. When I made a mistake in the test, it took me forever to find it. When there was a bug and the test failed, it took me forever to get back to like when that actually happened. So I was like, okay, I think I can write something to make that a bit better. So imagine a system that has 3 systems and 3 types of events. So a really simple system. And there's a rule such as when I do action A, I get 2 events, one kind of blue one and one red one. And the distance between the 2 is at most 1 second. So there's some tolerance, some propagation delays on top of this. So this would be like those events happen within a second, but then it's a distributed system. So you end up having to consider the fact that the thing that is testing doesn't perceive things right away. There might be some buffering somewhere, and you have to consider tolerances. But even if you remove that, so that would be a thing. So I run action A, and then I expect to see this from this system and that from that system. So if you try to just write that, oh, sorry, my presenter view isn't working. So there's going to be a few main principles and concepts over all of this talk that I'm going to try to attach things to. One principle, which it's kind of cliche, but making the implicit explicit. So I like things being explicit. So I mentioned the case of propagation delays. What I don't like seeing is having things in the code which are a mix of the actual tolerances of the test for like on the events and then just merge together tolerance delays, because that makes things really hard to figure out when you're understanding it. Like we had the same thing for some other parts of the system where people had timeouts and HTTP requests, which were a bundle of like, okay, how slow is the network? How long does it take for processing that thing? And then it was just one number. And then people end up just bumping that number because it's not explicit that there's a part that doesn't really change as the time to process a request, and then a time which changes a lot, which is the network situation, basically. So that's what I mean by that. And then I like redefining the key concepts, so not, I could have put this as just making things declarative, but basically if there is a concept which is, for instance, that is in the case before, like those two events in that order and with this much time between them, I like having that be a concept that is then both what's used when I'm writing it and what's reported to me. So so that's what happens if you use like transpilers. That tends to happen, is that you're writing your code at a super nice level of abstraction, but then you get the errors back. Anyone did some closure ever? Yes? How about those error messages when it fails? Like you're writing at a really nice level of abstraction, but then you're getting back stack traces from like, the Java implementation of the runtime. So it's really hard to map. You have to map back. You have to do all the mapping back in your head when something is not when something doesn't work. It makes it really hard. So for tests, that's something I wanted. And then what are those concepts? So the main concepts are going to be ordering. So what pieces of ordering between two things are strict. I want them in order. Sometimes I don't really care what order they come in. For instance, if they come from two different systems, usually there won't be strong ordering dependencies between them. Time itself and dependency. So sometimes there are dependencies. I do expect one thing before the other, and sometimes I want to do an action only after something has been perceived. So those are going to be things. So as I said, for order, there's going to be tests of the form I expect X then Y, or maybe in any order. So those are both related to order, but it's going to be explicit. And then time. So as I said, there's going to be basically at least two timelines. So we could smash all the systems into one timeline, as in like when things happen. But there is going to be when things are perceived, which is always going to be a different timeline. I'm going to want to be explicit about which one I'm talking about. So I gave you those examples already. Dependency, so usually they're sometimes tests involving hardware, so they're not as nice looking as unit tests where you just do like one piece of setup and then one action and then one like verification of what happened. Usually there's going to be some setup that you actually want to leverage for a few things. So the tests are going to be a bit longer and have phases where you do want to, like, once the first phase is finished, you start to do something else, and then you do whatever and you verify, and then a few phases of those. And then there's going to be a dependency between when things are matched and when the following phase is started. So what does this look like in F#? So imagine we're basically going to, I said there were multiple systems, but we were basically going to mash them all down into one single timeline so that it's not too confusing. So basically, if we want to verify the rule that I had before, so we're going to have to find the events. So that can be done rather easily, whether you do it with a functional kind of style, and you try find or you find index, depending on what you want to do afterwards. And then you're going to want to extract the timestamp from each of them, and then you want to look at the difference between them. So it can look something like this. So you're going to find and then have some matcher for the event that you're interested in, and then you're going to do this. But the problem is, this is it's quite a lot of code for a very, very simple example. Usually there's going to be more dependencies. And so if you didn't have that test here, that means that you don't care about the order. But again, that's really implicit. So when you're reading a test, you need to just go and look at every single thing that it does. So could we build some higher order function that is basically looking at two events in order or not and give that delta? Yes, and you could kind of get somewhere with that, but like when I started writing those tests, people had been writing similar tests for a while, and it was nicer than just this, but it wasn't nice. It wasn't as nice as I would expect. So, and this was a very, very simple case. So it didn't look that bad. It actually fit a PowerPoint slide for 2 events. If you had 5, not awesome, could be shrunken down. The worst was really the error reporting. So when a test would fail, you would have to like look back and then be like, okay, if we got to that point, that means that we found them, maybe not in that order, and then you have to look back at the traces of all the events coming in. It was, I'm not smart enough to I wasn't smart enough to troubleshoot those failing. But then the worst part of this is that this was dynamic, so everything was coming in out of order. It wasn't just like, oh, here's a list of events that happened, does it match? Because it was as part of like doing the setup, like running the actions, and then coordinating with the next phases of the test once it's passed. So it was, every test had to do that, basically. There was, the helpers were not helping that much. And then as I said, usually, so this was, I simplified one scenario that we had. So there's some jargon in there. So let's imagine this is access control and there's a door and there's a reader, and there's a sensor that gets active when the door is open or closed, and there's a request to exit push button when you're leaving. So this was a test because this test was verifying the really ad hoc logic that no matter the locking state of the door, if you're allowed and the door opens, as long as it's open and someone presses the button, there is no event on that. That is shunted, as long as the door is open. But, because you really don't want to re-unlock the door sometimes, because if there's like a strike going out, that's not awesome as the person is going through, the strike is just pulsing out. So that's one of the tests. So presenting a card of someone that's allowed at a reader, once it's unlocked, activate that open sensor so the door is open. Then when you open the door relocks, but it's still open. And then you activate the sensor and you verify that you did not either unlock the door, which would have pulled out the strike sometimes, or produce that event. So the test isn't as complicated as it seems, but writing that is quite a lot of code if you're writing it by hand. Like there's quite a few steps to be gone through. So I thought, okay, I can do better than this, if only to help me. And it seemed not that complicated to do to like declaratively write that. So what I really wanted was the two timelines, specifying when the order mattered and when it didn't, because that was always a mess to see. And talk about distance. What I also wanted to see was to maybe encourage building kind of a vocabulary of some of those patterns that we had there. So some of those things come into multiple tests. It's like I don't expect either this or that. Like those 3 should never happen for 2 seconds after this. So building a higher level of vocabulary that people could reuse in the test, so encouraging that. And then the last one was really the critical one I wanted, was when I messed up writing a test or someone messed up in the implementation and it failed, having a nice report of like, okay, what events came in, what parts of the rule matched successfully, like how far did it get that was great, and then when it failed, why did it fail? Like, is it because we couldn't find something? Is it because we found something but it didn't have all the properties we expected it to? Or it was a bit too late, or it came in after the reception tolerance? Like, debugging distributed systems is hard enough not to make it worse. So that's what I was going for first, and the first prototype was written really for that. So that was straightforward enough. So there's one type of things, which is a linear kind of pattern, where there's A, B, and C, and this will match any sequence of event where at some point A matches the event E1, B matches an event E2, and there might be anything in between. We don't care what other things happen in the system. And then after that, anything happens, which is E3. But there's that ordering, like it's in that order. And then there's the other part, which is out of order. Like any order matters, but I want each part to fit. So I can have any linear part, and then, yeah, there exists all of 3 matches. So if there's a sequence of events, I can match L1, I can match L2, and I can match L3. But there's no, or I don't care if L1 matches first, and then L2 matches second, and L3 matches third. So that kind of worked. So it looked okay. So let's say on the left is kind of what the language looked like, and at the right is a sequence of perceived events where the first one is kind of time. It's just 1, 2, 3, 4, so they happen in that order. And it's kind of, so I expect in that order to see something that matches hello, something that matches how are you, and something that matches bye. So that, like, first one matches, second one matches, third one matches, skips over an event, that's fine. So I was pretty happy with myself because that was really easy to implement. And then if it happened in this order instead, well then it failed at that second one. So I would have a report that would say, oh, we saw one, how are you, and we skipped over it because it didn't match hello. And then we were looking for how are you, and we didn't see it because 3 and 4 didn't match. So that was also it was much better than what I had before. So I was happy with that. So I just kind of plugged that in, and then those would be ignored, and that would fail like that. Concurrent also worked as expected. So then I expect ABC 1, 2, 3, but I don't care what the orders are. So if we perceive 1, 2, AD, 3, C, that matches fine. So that was also very nice. But then it wasn't enough because I wanted to talk about the distance between the events that would match. So you have to imagine that, like, expect and all of this, there are cases in distributed union. I can show more. So expect looked like this. Then you see kind of some other ones beforehand. So it was just something that's something implemented. So we introduced the word expect to mean like the testing case, and then we added a new piece of vocabulary, which was before. So we could say expect A, and then before 50 milliseconds expect C, and then expect B, sorry, and then expect C. So basically there's a big ordering dependency between that A comes before B comes before C. There's a time dependency between A and B, but there's no time dependency between B and C. So again, that worked well. And then we had kind of the expected thing. There was also after to say, like, we don't expect this to move forward until after sometime. That worked. So it looked like this. So we could say expect hello, and then shortly after we expect the second one, but then the third one has no dependency. Does that make sense so far? It's very trivial. I agree. And then, so basically it would match those two, and then look at the constraint, and then go to the third one, and then it would match. So that was basically what it looked like now. So there were some semantics to be defined. So if you had an expect and then a concurrent, basically the meaning of this was taken to be that the first one, that between whatever we matched for A and the last thing that we matched out of all the branches, that there would be less than 50 milliseconds. So that seemed to make sense, which what we expected. So basically we said that concurrence time was the last one, was whenever we matched the last one of any of the branches. That was also fairly natural. Sometimes we were rejecting. So we were saying, okay, we were going to try to match all of the things in there, but we don't expect anything matching A. So as in the case before, like we're going to do all of this, and whatever happens, we're not getting a door unlocked event. We're not like getting a request to exit event, or we're not getting a door unlocked event. And that worked well. We added some combinators to compose things into A, which we never needed for tests, because you never want to say, I expect this or that. That's never what you want. But if you're rejecting, you might want to say, I don't want any of this or this or that. When you're writing a positive case, you need to know what you expect. You can't be like, oh, maybe this or that, or maybe that type of event or that one or that one. That's never really a good case, but once you're in a negation, that actually makes sense. So we added that, so it worked well. And then I sat down, and I was pleased because I'd fixed one of my problems. So it was more declarative. It definitely took up less time. Less time to write and to analyze failures. It also solved the reporting problem, because I had a basic HTML report produced from that, basically showing which events have made the rules progress. But it doesn't solve the part where we're going through multiple phases. So we're doing all of those steps, and then we expect the door to unlock, and then we're doing all those steps, and then we expect the door to unlock. But then we expect it, and we do all those steps, and we expect it to not produce that given event that we had before. And the problem with that is that those phases. So you're running some actions, and then all you're doing basically you're saying, okay, so capture the events asynchronously, and then match this part of the specification. So you're saying, okay, run the present card action, and then wait for 2 seconds or whatever, and then match all the events you've received from the systems in those 2 seconds with this spec. And then you could do the other action, because now you know if you match it, you're good, and then you keep going. The problem is you have time in 2 places now. You have time in the spec. You have your tolerances in the spec, so I expect this before that. I expect it to unlock within 100 milliseconds, because otherwise people will get angry. But then you also have basically at the control level, you have to say, okay, wait for 2 seconds to accumulate events, because it's hidden, like it's in 2 separate places. There's the test itself, the control part of the test, which is running the actions and capturing the events, and then running the verifier, running those spec on the events it received, but they're completely separated. Like, it's not aware of what's inside. So what that leads to is it actually looks like this. So assume you have a function called run, which takes some actions to run, and then a timeout on how long it can possibly take to verify the spec, and then verify the spec, and then move on to the next phase, and there could be a few of those. With another obvious problem, there's one, which is maintenance. Like, it's a pain, because if you're bumping a timeout inside the spec, you have to remember to go back in every test that's using that and then kind of bump them out, because now it's possible that it takes longer, you have to capture a longer period. But then it's basically making that timeout have to be the worst possible case. So, which is okay if your variance is low. This is not too bad. Like, okay, if your median is 10 milliseconds and your 99th percentile is 15, sure, run it for the sum of all the timeout. It's not too bad. In this case, so there were timelines there. Some of those are like acting on hardware, and some others are perceiving from hardware, and some of those are systems that buffer stuff and then have to synchronize data to another system, and it does something. So your variance can be really, really, really high. So what we ended up having is that you had to, maybe the test, the usual set of events that you would match your spec against would take 50 milliseconds, but your timeout was 2 seconds. So you had to capture events for 2 seconds to make sure you had them all. Then you would verify, and you're like, yep, we have this all within 50 milliseconds. And then you could run your second phase. So tests took as long to run as they possibly could. Always. Because there wasn't a way to shortcut. Because the thing that was accumulating events didn't know about what the spec was. So that was after the first, I thought it was clever, and I had solved my problem as a programmer, that I was writing tests and it took less long. Well, then the test runs were running overnight, and they still took as long as before. They still took like hours and hours to run, which is not awesome for tests. Does that make sense as a problem? Okay, so we had to illustrate this, in case it wasn't, so let's say you have an action there and an action there. Even if you're matching the spec here, you have to wait for long before you do your other action. But you, like in theory, you could run it that way. As soon as you've matched the first part, the first phase, you move on right on to the other one, and you can keep going. And then it's pretty obvious that you basically have the best case scenario as far as time goes. So this was like, okay, this is kind of impure, because before we were just like specifying a nice spec of what we expected. And then we're like, well, let's add some coordination into the picture. So what I added was just one new word, which was to trigger a future. Basically, like, give it a future, and then when the verifier is matching that, trigger it. So then you could have, like, your part. So you could, in the test, say, okay, once you've matched spec 1, trigger this coordination point, and once you've matched spec 2, trigger that second coordination point. And then within your the control part of your test, instead of saying wait for 2 seconds, you could say, okay, wait for chord 1 to trigger, and then keep on going. So that's what I just said. It was nice, and this is actually the first historical remnant that I found in the email that I sent to someone. So it looks kind of nasty, and it is, but it was much better than it was before. So here there's like CCR. We didn't use async because async was slow back when we started. Well, the thread pool was slow back when we started, so we used the Microsoft Robotics control and concurrency runtime. And we wrote a workflow over it, and it's still in prod. Anyway, so what I was actually working on at that project was basically controlling jetways for airports. So basically they have codes that they punch into keypads that say basically we're boarding 747, and then that says, okay, you're opening that door over there and you're making that go into a lockdown because if someone opens that door, they're going to fall on tarmac. And there's all kinds of rules like this. So this was one such test case. So basically the test was reading a card, like presenting a card at a reader, well, configuring everything, and then presenting a card at a reader, and then there was one coordination point here. So it needed to be defined beforehand, of course. So there would be one defined there, and then the action would read a card and then just wait on that to happen. And then something else would be accumulating events and then matching, when is that? Okay, so the trigger is here for that one. So this is a concurrent one where we expected to get a credential read event, then can you see anything? What's happening? No, okay. So it's a pretty big mess. The point is, like, there were this coordination where the spec knew how to communicate to the control part, okay, you can move on now. Which means that instead of waiting, we could now just say, okay, as soon as we got there, we move on. But this was very repetitive, so you had to define all your coordination point in advance, trigger them, and then you still had it kind of all over the place. Well, in 3 places, but it was still more than one. So we said, okay, like, let's not see this as a spec timeline thing anymore. Let's just say it's something to write tests. It's a DSL to write the tests in. So we'll include both the control part and the rest. So we'll add something to the language called running an asynchronous action. And then it will be run wherever, as soon as we've got to that point of the test. And then we'll keep on matching. So it was basically built from the trigger, but it removed those 3 points, which made reviewing fairly difficult. So it now looked like that. So an action, which would just be run, then would just be run, actually just fire and forget on the thread pool. And then we would expect to perceive something. And then the other action would only be run once we've expected. So this didn't add much complexity to the thing that would run this, which I haven't talked about yet. Because it was basically just automating defining the future, triggering it, and then running the action. At that point, okay, so before that was all like the first prototype that I built, which was, like you saw my initial vision for this was very, very narrow, so it wasn't necessarily, it didn't age super well. So right before that is when I handed it off to someone whose job was actually coding the company. So I said, hey, you want this? You like F#? He already did F#, like he was a day-to-day F# programmer in one of the projects. But this was a new kind of thing for him to work on. He's the one the smartass who named the project. So he started extending it to support that, amongst other things. So as I said, it was abandoning purity. It's not really, it was just expanding what the domain was. Initially, I thought the domain was just like those little nasty pieces of the code that were like looking in a set of events and then just comparing some subset of things amongst them and not comparing some others. And I thought that was the problem. At that point, I realized that's not the problem. If you want to really solve it, the problem is writing is the whole test writing experience. So I changed the domain, basically. I expanded the domain. So this was, initially I didn't want to, because I was like, this is this is not what this is about, this is not what this problem is trying to solve, then realize it wasn't really useful. So don't get stuck to your domain, would be one piece of advice. And then, so this was one set of things. So the main concepts was basically you have one timeline forward, you have some expectations which were just passed an acceptor function that would be run in the events and it could accept them or not. And then there was some coordination, explicit coordination, which was triggering a future or using the action keyword. So how was this implemented? So the first version was really straightforward. So it couldn't really move back. It was really just at a point that it was matching, and then it would read stuff from CCR port, which would be an async channel now that this has been released publicly. So it could just receive that and then try to move the rules forward. And that was the piece that got the tolerance. So it could be told, okay, the max time we expect to see for propagation is 2 seconds. So if you're expecting an event with a timeout at midnight, 2 seconds after, give up. So this was also nice because this was something else that was very messed up. And the reporting that you would get from the test is it would say timeout, but you didn't know what that timed out. You couldn't tell what it was waiting for and which were the components. And we could also wait less pessimistically as before. So we also had, what I also wanted was those nice reports, as I said. They look very ugly because I still live in the 90s, so I just know how to do tables in HTML, so that's what it looked like. So basically it would show all the events that were received, when they were received, what was the time in the event. So this is a case where the system under test is further along the thing testing. And then it says which rule match test which rule it was seen. So you could see like some events that were matched, that were not matched, well, that were matched but were rejected. And then you could see it. So you could see it on the event timeline, and then you could see it from the rules. So it would produce both. So if you could choose basically which view of the test was more relevant. And then, so yeah, this is kind of a choose your own adventure part. So since there was one prototype implementation, which I just described, I don't think it's very interesting to talk about. There is the first production implementation that colleague did. I can talk about the approach that he took and some limitations in there. Then there's a second of this. Okay, about that same implementation, some interrupt with C# shortcomings that I only found out once I started trying to make this usable from C#. And then, as of mid last week, I realized some shortcomings and bugs in the previous implementation, so I rewrote it. So that's a success story for F#. I just rewrote it, and I think it took like 2-3 hours. It's like a fifth the size of the previous one. I can't show that one. It's pretty nifty, and somehow it works. So I can also talk about that one, which might be the more interesting one. So, show of hands, who wants to read about the last one? Okay, cool. That's what I thought. Interrupt shortcomings were basically just passing way too many parameters into a function, passing lambdas, the typical kind of thing. The approach limitation was basically as the language extended. So basically the last implementation, the main approach I've taken was to define a much smaller core language and then basically compile the big language, the big impure language that this had become into that one. So then the actual verification logic could be written in terms of the small language, which is much more tractable. Because some of the bugs that there were in the original one was, it was small enough at first that you didn't need that distinction. The two languages, they would have been at about the same cardinality in terms of like number of keywords and concepts. But then as it grew, like that guy didn't introduce that split. So he basically had all of that, every time that language expanded, that expanded the complexity in like 5-6 different parts of his thing. So then there ended up being bugs such as, oh, if you have an action nested 3 deep, it doesn't work. It's like, and it's not that the guy isn't smart, it's just like, by not introducing that split, as that language grew to be, because the point of that language was to be pragmatic. It was not to say, oh, I found an atomic language for tests. It's just like, let's just encode the patterns that people actually need at our company so that they're more efficient. Like that was the goal. It wasn't to do something great, it was just to make something that helped them. So we kept expanding the language, but then every time that happened, like his life became hell. That implementation was very convoluted, and mine isn't. The second one I did was not because I'm smart, it's just that I saw where that complexity was and I was just like, okay, let's just try cutting it there. So right now I have kind of the same problem I mentioned for the closure stack traces. So now the errors are reported in terms of the small languages, so I have to build source maps. It's a to-do item in there. So yeah, so basically, okay, that's not interesting if we talk about the other one. So that is the, so this is the language as a whole. So there's before, after, in between, which are basically about the distance between events. There's action, which I mentioned. There's within, which takes a branch and basically has a constraint on the first, between the first one and the last one. So you could say within 5 seconds, those match.
Can you make the text bigger?
I can most certainly do that, and you do not need the output window. I understand you don't have many pixels. Is that better?
Yes.
Is that readable? So, assert is another one that we added that seemed a bit impure, but oftentimes that's what people needed, was just like something, and with a description string so that people could see what that assertion was. Then there was something for tweaking the reception tolerance in the test, which was often because we were now looking at the different, we knew we were looking at a timeline on a different system, which had slower propagation delays. Then there was rejecting, which I mentioned, which is basically we expect to match all of this, but never match this. And rejecting for, which again looked fairly impure, but was very useful, which is basically okay. Especially when we were looking at things. So some of the things tested with this at first were logic for things like alarm systems. So like you have sensors that activate a zone, but then you have a threshold of how long the person has to walk to there, and then if they write the right code, then it basically forgets all the events before, otherwise it triggers. So it's kind of a large, very ad hoc, not mathematically sound kind of thing that people expect. So lots of tests for the scenarios that people expect are very useful, because that's when you know you've actually done it. Because those things were built over time, like both in the access control and in intrusion management. The things that happen is that those are systems that are where the specs have evolved over like 30 years, and basically by manufacturers getting a call from someone, and then you're like, okay, sure, we'll tweak the custom like PLC to if we have driving your thing, but then as you move on, people have expectations, which is like, well, those don't really fit together. It's like, we don't care. That's how we train our security guard. That's how we built our like central system there. That's how people expect it to work. So you can't really say, well, we could build a much smaller set of rules that would be nice, and then we could just do some property-based testing on it. Like it's, you need the scenarios because the model is kind of nasty. So that's the big language, and then some. There are some tests in it. So those are not like, those are those are tests for the verifier itself. So like matching 1, then 2, 3, or 3, 2, and then 4. So that's what it looked like. And then, so the verifier, the previous one was apparently 1,200 lines, because that's where module prototype starts. So it's called microcode because that's what I was thinking was how CPUs work, which is they don't implement the big ass i3 x86 instruction set. They have a much smaller microcode, and then it just interprets it just as it goes. Okay, so now I have a problem because my comments go too far. So it's a smaller thing. So basically, it has concepts of. And it's not a small, I know how to make it smaller, the font, the language itself. So there's expecting with no upper bound, which you sometimes need. There's expecting with a timeout that is hit, this is the delta to the last event that was matched. There's rejecting, which is basically forever after in this branch. You don't, if something matches this, you bail out, the test has failed. There's delay, which is basically don't move forward until that much time has passed, which is mostly used, it's not used in the language, it's used when we're compiling stuff down. There's a side effect, which is basically just triggering a side effect on possibly the last event matched. It's an option because you might be at the beginning of the test and you haven't matched anything, so there's nothing to put in there. And then you can see there's no concurrent and there's no rejecting. There's a rejecting. There's no concurrent. So what we have is we can start kind of nested branches and they can recursively start other ones. And you can join with a timeout, which is basically wait for all of them to have finished, possibly with an upper bound. So that's nicer to like write down the semantics on a piece of paper than the previous one, which was a lot more add-on. And then the way this works, there's basically two functions. So there is one, which is, I'm not used to the font being so big, which is process events. So okay, so at any point of time, one branch has two pieces of information. It has a state, and it has the instructions that are yet to be done. So basically, this is the progress, and we move forward depending on the state. So process event is basically the one that is called, that you would in practice call to make it try to move forward when you got an event or when you feel like you should give it the clock. You should say, hey, it's midnight right now. Like, does that make you move forward? So that's why there's those two pieces of information. So there is the current time, and there's possibly an event. So basically, what this looks like in, if you want to run it, so if you want to run the new verifier on a set of operations and data, which is a sequence of events. So you've captured the whole thing, and then you just want to say, okay, does this match the spec? Like, there's no asynchrony, it's just, does this match? You can just, it's just a fold on process event. That's all it is. It's just folding, and then maybe at the end, the state it says that it's finished. The more interesting one is the asynchronous one, which basically just, so MB is where the asynchronous events are going to come in. And then we're going to receive with a timeout. So we're basically going to tick every half second and then accumulate all the events. We're going to keep all of the events that have happened up to now. Because one of the things we want is we want to accept that the events may come in out of order since they come in from multiple systems. So the reception time might mean that an event comes in after another one. So that was another of the shortcomings of the main shortcoming of the implementation. It didn't do this quite right. So what I said is, okay, I'll just make process event idempotent, and then I can just throw all of the events at it over again. And if that makes it progress, because an event comes in late, but within tolerances, it will move on forward. So we keep track of all the events we've seen, and then the state that we're at. And then we do the same thing as before, so we just fold over all the history. If we've gotten a new event, we pass in the whole history with a new event added in. And if we haven't, we just basically tell it the current time. So if we have something like delay, which I said is don't move forward until this point in time has passed, then it's only when it ticks that at some point it will tick beyond the delay, and then it will move on forward. So that's it. The nice thing is that all the asynchrony is now captured in this one. Before, the asynchrony was kind of at the root of the verifier, was like receiving an event waiting for an event with a timeout and then trying to be clever. So this says, I'm not going to be clever, I'm just going to make sure that I can pass it past events again, and it won't care. So process event is basically responsible for knowing when things can move forward. So there's a shortcut, so some states are terminal, so it's either they're failed or they've succeeded, so we don't do anything from that. If that's too many details, just tell me. I figured that's the F-sharp part is looking at F-sharp code. So it's actually doing something fairly straightforward. So it's only looking at what can cut off things. So if it's rejecting, if we receive an event, so there's an event, and one of the rejecting things we had in the state matches, then we bail out. That piece of the thing has failed completely. If we were waiting for anything and there was a timeout on that, just bail out the clock that we've been provided here, the wall times we've been provided, has passed, don't care. And then the other one, so basically if we're waiting on an event and we match, then we'll advance. If we're waiting on nested branches to complete, which is a join, and all of the branches are done, so they're all in terminal states, then we will update the state, and then we will advance. Then we'll fail, then we don't need to advance because we failed. So process events is basically dealing with just knowing when we can progress, and then advance is the one that understands the commands. So it's basically moving forward and updating the state to reflect what operations have been run. So if we get, for instance, the easiest one would be which one would be the easiest one? To reject. So if we're running reject of something, then what's left to run is everything that's after. So we've run that operation, and then the state has one more rejecting function, which is what has been passed, and then we move on to the next one because we've marked that rejecting thing is now in the state, so we can move on, run another operation. But then if we're actually waiting on something, so if we say delay, we're not advancing from there. So we're still, we're just saying, okay, the state is blocked, the progress is blocked on this one. So this actually works really well compared to the previous implementation, which was basically trying to transcode, but it was transcoding from the language into something bigger. So it was kind of the right intuition of making a split, but it was basically the verifier had become, what I think happened is that the verifier had become very complex as the language grew. And then that person modeled that very complex thing in that secondary language. And it made some things easier, but mostly it just made it more confusing because it didn't really reduce the complexity. Meanwhile, these are, to me, they're much simpler, and I haven't found a bug in them yet. So that's a few hundred lines of code. And then there's a compiler, of course. Compiler that really just composes. So those three go down to just one thing, which is the side effect one. So an action is compiled to the side effect of doing a fire and forget event, async action. A trigger is just calling that function. An assert is just running, if not the check function, then raise an exception. So that's straightforward, and then the rest is basically the expected stuff. So rejecting with a branch is just like starting a branch in which we reject, and then compiling recursively what's inside, and then doing a join on it. And it's all reversed because I'm building it using lists, so I have to do everything reversed. Why not? So most things actually compiled to, the only more complex one was the expect, because it depends on what's been seen before. So basically you say expect A, and then you can put in a bunch of before 50 milliseconds, and after one, and you can put in all those, and then it's when you add the other operation that it applies. So that's the only real part of complexity that this has, is those three cases where, if there was no constraint either way, it's expecting with no bounds. And otherwise there's, if we're saying after a second we expect it to progress, then we're basically rejecting progress for we're starting a branch which rejects progress and moves on after 5 seconds, and then we're joining on it. So it will wait 5 seconds, and then, or if it comes in, that branch will fail, and then the join will progress right away. We'll say, oh, one of my branch failed, so the parent branch has failed, and then it will just all go down. Then otherwise, after 5 seconds, we'll be like, yeah, nothing that has been presented to me has made me fail, so we've succeeded, and then the join will continue and go on. So that approach worked fairly well. Most of the tests are passing. Most of the tests that were built for the other language are passing. Does anyone have any question on the implementation? Or the approach? Because it seemed to work. Yep.
You worked with Erlang before, right?
Mm-hmm.
Okay. Do you think someone who didn't have that experience with Erlang could have come up with an approach like this? Or would they get lost in the weeds and not know that there's a very simple way of looking at it?
I'm not sure, and I have the benefit of, as I said, I really only discovered the limitation of actions not being run if they're too nested, and the order being the out of order stuff not working well. Because I looked at some, so describing, I looked at some tests written using this, the previous implementation, and I was like, what are those people doing? That's not the way to use it. That's a really just why? Did you just not get the point? People are like, well, we did get the point, but there was a bug in the implementation, so we kind of
How to go around it?
We went around it. We used these awkward sentences in the language to kind of work. So I came back to this after, I guess, 2-3 years. And I was like, oh, obviously that's the way to write it, and then it worked. So I'm not sure how much is the background or just the insight of having at that problem slowly in the back of my mind for a few years, and then because that was my last slide of the before I did this was current problem. The current verifier is very convoluted. Possible option, try compiling it down to a simpler language. So I as I wrote this slide, that's what I was thinking. This would probably work, but probably not worth it. And then I tried it, but again, I've been sitting on this problem for a few years, so it was. I'm not sure. What do you think?
Oh, it really has to do with what you feel your experience is.
Yeah.
The thing I was starting to see is if you've done a lot of Erlang, you start seeing that there's a very simple approach to things. You let the language do this lifting for you, and you just sort of express this stuff, and it will do the stops and restarts, and it will do the joins and all that. And you said, wait, I'll just write this little thin Erlang layer underneath this, and all this stuff is fixed.
Yeah. From that point of view, I think very much so. And this was, and I think even more, because the actor framework that we built on top of CCR was very limited. So all of the nice things that real Erlang has versus some kind of message passing thing, all of the key differences, such as what you described, the very declarative way to monitor a process, and then a library can say that when you're sending a message to another one, you're monitoring that destination process, and so that if it dies, it shortcuts right away. We didn't have that. So I was used to that from Erlang. We didn't have that in the kind of in-house framework that we had. So I think those things, I was missing them very consciously as I wrote all of that, as I wrote the big, massive project, those, which I think are very key elements. Mm-hmm. You only feel them when you think you have everything, and then you realize, oh no, that's not quite, the key part isn't there yet, which is really the monitoring is a big thing. If you don't have the identities, the way they've built the identity being a process is pretty key. So I think those missing points, I had them very clearly in my mind. So when I was seeing this, I was like, okay, that's the key thing that we need is the right level of abstraction, so that it's, because that's what happened when you use Erlang. You send a message to, you do gen server call of another process, then it tells you, hey, it failed because the process died while it was processing your message. oh, that's nice of you to tell me. I don't have to go look at the traces of that process, see if it's my message that caused this. Then like it's a lot of that kind of heavy lifting that is very tedious to do for a normal baby anyway. It does it very nicely for you. So like finding the right concepts is always, it sounds very trivial to say it like that, but it's a big part of the success, I think.
Another thing I noticed was, it seems like what you've described is shared by other DSLs. There's this language that you're writing, and now you need to have a way of reporting on it and things like that. A lot of the same things you're talking about, it reminds me so much of like fparsec, which is a parser combinator language. And it's sort of like you're parsing an event stream, and it seems so similar in some ways, but in other ways you sort of had to go off this way because it's a little different, and I get that. But one of the things that happens in like fparsec is you have these things where like the bang operator, it's like, I'm throwing up an error right here if I hit this point, you know, and I'm naming this so that when the error message comes back, it's called, you know, solving, you know, trying to find the noun, as opposed to, couldn't find space, couldn't find tab, couldn't find, you know.
Yeah. Yeah, well, it is very similar. It's not an accident when I described the semantics of the early blocks. I was describing them as regex on the timeline. Like it's, and that's.
It reminded me a lot of Berzozowski's derivative of state machines. I think you could actually implement it that way too. I'm not sure if it would be better or worse, but it's definitely like there's relation there.
Yeah, no, there's a lot of them. I kind of refrained from digging a lot into them, but it would definitely be interesting, especially now that we have kind of a small.
The core language could do that because now you've got like it's tractable. You've got one place to work on it, because you can't really throw any old programmer at that because that's pretty finely tuned.
Yeah.
But once the core is done, yeah, you could do that.
Mm-hmm. That could, and like as soon as you decouple like the programming surface, yeah, it's there's a lot more freedom. Like that was one approach, but I think that compiling it down and having a mapping back for the reporting, yeah, there's probably going to be. I'll find one of our clever people. Try this for this part. Yeah.
When you were working on this, did you have like a hardware test bed kind of like lab?
Oh yeah.
Oh, it sounds pretty cool.
It's very cool unless all the tests, when the tests fail, you're like, oh, what happened? Oh, a wire was slightly loose in one of the screws in something part of the lab, and then the wire is kind of half connecting. So depending on the vibration in the room, I'm not making it. It's really that. I was so glad when I went out of that team and I could just deal with like, oh, software systems. Like the failure modes are a lot more tractable than the tiny little screws that, or some people will just go. Some people went in. So they would, sometimes the controllers are from third parties and we can't control everything in them, and they beep. People in offices next to them, they don't like the beeping. So as long as the lab was next to the people working on it, everything was kind of fine. As soon as they moved out, some things started happening with the test bed. So some systems would become disconnected. They would lose their PoE. Who knows why? One would think our cameras could answer that question. Turns out there's no camera. It was interesting. But it's obvious. Something beeping repeatedly is very, very annoying. And it was next to support, so they're kind of at 3 a.m. fighting with our system to make it work, and then they have something like nagging at them. I understand them going and turning it off. So that it's really cool when you look at it and you look at the big blinking lights and a shitload of wires. In practice, it's a little bit a pain. Does that make sense? Because we're switching to C#. Okay. So that's what I said earlier. I think maybe last summer, that things were quiet enough that I'm like, oh, let's spend a few days. I think we could write something, because we have, most of our programmers write C#, including most of the people that write tests. So getting them to write their tests in F# just to get that was kind of it wouldn't happen. Like they weren't sure enough of the value. Because again, like you get, like, I started building this because I wasn't used to writing those tests. I started writing them and I was like, no, that's not, I can't deal with this. Like I can't write 100 tests with this. Like doing it by manually. It was too hard to get done. But the people that had slowly like they got used to it, and they got used to it, and they were fine with it. They weren't the one pushing for the thing. So if I went and saw the C# people and told them, oh, that thing that you don't even realize you're paying the price for. It's like talking about controlling mutability. You go try to convince C# people, oh, you wouldn't have all those problems if you didn't mutate it all over the place like that. And you're like, I don't have that kind of problem. I've heard that often. They're like, well, that's a tiny, like sometimes we have an all reference exception, but it's not that often. But it's only because you don't really notice, like it kind of becomes part of what programming is and you don't notice it. So it was kind of that same problem. So even though I thought it would bring value for them, maybe even to learn F# to do that, that pitch fell really flat for those people. But I was like, I think we can do something that feels kind of natural in C#. And obviously, feeling natural would not mean building F# lists of F# discriminated unions, and then kind of tacking them on, even if we disregarded the obvious thing, such as the async workflow, like those kind of things could be worked around, but that would be a nightmare for them. So yeah, so it was not, we could call, like, it's like all F# code can be called from C#. Not always will someone be willing to go through all the trouble that is. And I say that as someone who wrote said wrapper. It was nasty. And I wrote the initial interface, so I was fully to blame for all the rough edges of calling that thing from C#. So instead of that, it's like, oh, like the way people usually do this is using a fluent interface. So basically you have an object and then you call a method and then it returns itself, and as you do that, it accumulates some information. So like configuration builders are usually like that. So you'll specify some things and then it'll just work. It's usually like more mutable than it needs to be because the interface it's chaining. So you could return a new version every time and it would work just the same. But usually x.foo returns x and then .bar returns x again, and then you kind of think you haven't changed the original one, but you have. But people are used to it, so it's not the end of the world. In general, it's just the builder pattern. So you call some mutation operation, and then at the end you kind of freeze it and say, okay, give me that. So string builder is an example that's always used. All the very nice system collections mutable library is also used that way. It's kind of a limitation of the transients things that Clojure has, which is basically two ways. So you can go from very efficiently from an immutable to a mutable, then mutate it in place from a single thread, and then get very quickly get an immutable version again, which is a nice way to kind of control the mutation, but not pay all the price. So as I said, string builder is an example, and then at the end you basically produce an immutable object. So the immutable snapshot at the end would be that list, would be that F# list with all the things in it after it was done. So this is a spec builder that basically contains the list of all the elements that have been added, and at the end you have a build method that, whoops, spoiler. So I did immutable because I don't remember why. But there's a list of, so this here is the discriminated union. There's many generics because I didn't think of C# when I wrote it, so the generics aren't as meaningful in F#. But, okay, so those who have generics intolerance, be careful in a few slides, it might hurt. So basically at the end, if you have a builder, within it you can call build, and then it will return a spec, which is immutable, which is what's in the okay. So first was like, okay, linear branch, so just like things in order with possible restrictions between things. So that that could be made to look reasonable. So you could say expect A dot before 50 dot expect B. That it's not that bad. Like one might say even looks better. Like it's very matter of taste, but it's not terrible. Then you get with concurrent, and then you realize that you are relying on the F# literals to do some things for you, which is scopes. Mm. So if you're just calling things on a builder, well, you're kind of just calling things on a builder. it's always the same builder. You don't have like, oh, we're now level 2, now level 3, oh, back to level 2. So it's all good and well as long as you're just doing the first branch and you're like, well, now I want to switch to the second branch. What do I do? So that's not as obvious. Okay, so basically we use generics to encode where we're at. So those are the main states as we're building it. So we start with, in the kind of linear case, and then if we expect something, or we do an action, or we say before 50 or after 100, we're staying in that same case. We're still in the same branch. If we're rejecting, remember rejecting was basically giving an event X matcher, and then a branch to be run where we wouldn't expect any of those to match. So then we need nesting, because we're implicitly saying that. So we can call that a nesting branch, a nested branch. But then if we're saying concurrently, every branch of the concurrent is basically the same thing. It's a nested branch. It's a branch that like you're in it, and then it's linear, and then you can basically close it when you're done. And you want to go back to the state that you were at before, which would be kind of a third dimension there, being like where you were before, where it would point back. So from the nested branch, you want to close and then get back to where you were before. So this needs to be encoded in the code. So basically, every nested branch has a function that it can call to return its predecessor. But then those have to be in the generics. So the generics give you an history of where you are in the thing. So it basically looks like this. And then you have extra generics because of the test and the event being generic, and the test being generic in the event. So that is, it doesn't fit on the screen, by the way. So this is the signature for open branch, which is basically like you're opening a new level of nesting. So if we cut off just some of the redundant stuff, so the predicate and the message are also useless, so we'll remove them. Because, okay, first I just removed the fact that C# wants to see the generics everywhere. It wants to see them at the type level, the method level, at the parameter level. Don't lose sight of the generics. Like, you can't. So if we just remove that, then we just have some like not needed stuff from the DSL itself. I mean, you're seeing the message and the predicate and the message everywhere. So if we remove them, it starts to be a bit more understandable. If you remove them, now it starts to make sense. So basically, I'm not sure if it's visible, but open branch has type nested branch of concurrently node of branch. So basically, where this comes from is from this here. So the type of open branch there, it produces a nested branch that will return into the concurrently node that will return into the linear node before. So at every step, like the type that you have, the nice thing is that it also constrains what you can do. So if you use IntelliSense at any state, at any point in your spec, you only see what's valid within that state. So it's disgusting, and that's it. Like it encourages not nesting things too much. And actually, there is one part that just pulls in a whole spec as is. So if you split it in that way, you don't see, because most of the generics they disappear. Once you close your builder, all you get is your message type and your test type. You don't have much. So if you break it down and you build like elements of the language that you then just pull in, you shouldn't get too much nesting, so the generics shouldn't get too much out of control. But I haven't found a way to avoid this. So it kind of looks like this. So you spec that basically creates a builder. And then you can say, okay, while rejecting, reject, expect this, expect that, and then close, which brings back to the previous level. Build freezes the spec, so it produces basically the list that goes into the F# thing. Then verify async is a helper that basically takes those messages that have happened and tries to push them, and then get timestamp for other reasons. Because timestamps are not in the message, and we don't have type classes. So basically, we pass to the verifier a way to get the timestamp from any event instead of wrapping everything. So this doesn't look too terrible. But there's something interesting, which is, and it could have been built another way in F# to have the same property. But the way it was built, which was basically for efficiency's sake, being able to leverage the literal as much as possible, is that by leveraging the list literals, basically putting two words next to each other in the language is that's done by the compiler. And any two things fit next to each other in a list, as long as they're of the same type, obviously. But like, you can put 1, 2 is a valid list, 2, 1 is a valid list. Like, you can't inject a constraint in there. So since we use basically const as the way to build up the language, we can't put in any constraint in there in which words fit next to each other. So before, like as I said, you can't say nothing and then, oh, before 50 milliseconds, something. That doesn't make any sense. Because you need to have matched with something before you say, you put in a distance constraint. So this was verified at runtime. In C#, with the way I built the C# one, you can actually encode it. Because we're making that composition point is explicit. So that's an example of what I just said. So we can add a new state that's an empty linear branch. That as soon as you expect something, it goes into the previous case. But then you just don't put those methods are just not there on the first one. So as you're using IntelliSense, it just won't give you those options until you've expected something. And this we could have built it this way with the F# one as well. We could not have used lists and then just have used like function composition pipelines or workflow even. That interface has gotten some use, so it has some inertia of moving forward. But it could have been an option. But I just felt it interesting as I built the C# one that I actually could verify more things at the compile time. I could actually help the person more at runtime. With some costs of decoding some nasty generics. So the C# version basically, here. So there's some nasty things to build the basics, but mainly it's just adding. There's in the accumulator we just do all the creating the trade union instances by hand. And then does this contain just this just contains kind of the base thing that everything does. And I think here is where we have all the branches. For instance, a concurrently node, which has a parent type, which is where all the nastiness came from, which is the type that it will return when we close it. The type of close is the type of the parent. And it's basically every time you say, I have to scroll because it's C#, every time you open a new branch in the concurrent, once that branch is done, we add it to the list of branches for that one, and then once we close it concurrently, we close that list, and then we go back to the previous one. So this was not fun to write, but it wasn't that much code either, and it was just one. So all that's left is the leftovers of the types of integers. So, any questions on the C# part, by the way? Or did that kind of make sense? I thought the result is not terrible. It's better than I expected. I think it's very usable. The sales pitch is better than it was. Not entirely successful yet. I have hope. So that also included ripping out all the CCR stuff, but it wasn't before because that wouldn't work well. C# and putting it async and fun times. So we have seen a reduction in code size. But interestingly, one of the things we've also seen is that before tests would tend to be a mix of overfitting and underfitting. So the part that it was checking sometimes a bit too closely, more closely than it needed to be, because of the hierarchy function that they built to build a test out of. So some parts were like more strict than it needed to be. So they would fail sometimes, like, oh, we don't actually care. Like that one could have been in any order. So then usually what would happen then would be that it would be made too loose. By removing that, it'd be like, well, we have no function for like those two in order, and then that one not, and then this one. Like, it was really hard to encode all of the different patterns in different hierarchy functions. So the nice thing about that is that tests ended up being, like you could read the test and basically know what's a natural constraint and what's not. So that was, I like that. The nice little reports were very helpful when you have like 100 events coming into your test that make it move forward. The tests in F# basically use a lot of yield bang in yield to pull in like sometimes a whole branch that is a pattern in the domain, like in the domain of the thing that's under test, in the domain of like intrusion detection. Maybe like that sequence of expectation with those tolerances is used in many tests. It's a thing that the experts would talk about. So then you can just yield bang that whole sub thing and it works. So that encouraged a lot. And same thing for the actions. So you basically have in most of the test projects an actions module and an event module that would be just like building blocks for those. So people started composing them a lot more. They did it to some extent before, but it wasn't as natural because like those are just lists of, as long as they're of the same type, you can just like pull it in and it works. So that happened more. I can't quantify it. Reduction in code size was probably a 30-40% for those parts of the tests. And the biggest thing, which is the thing that I wasn't trying to solve in the first place, which might be a lesson, is you might be off as what you're trying to solve, is the runtime was probably reduced to 20% of what it was before. So reduction factor of 5. Mostly because, as I said, like the variances were so high that things that were pessimistic were really, really, really pessimistic. It wasn't just a little bit pessimistic. It was like, let's wait 3 minutes. Because sometimes it can take 3 minutes, so let's take 3 minutes. And oh, it took 2 seconds? I don't care. I'm waiting 3 minutes right now. So that was unexpected, but it was a big thing. And surprisingly, people haven't had too much trouble learning this. Like, they've had to get around to it, but it wasn't too bad. And like coming back to why this makes sense for an F# user group, I would never have done this not in F#. Like the initial impulse would not have been there. Like the C# version, I wrote it, but I had a clear idea in mind. It was like, I want to reproduce this thing and make it like look natural, but I had a picture in my mind of what level of abstraction I wanted, what concept I wanted to map to. I don't think I would have. Like, and I've built some of those before for other stuff, like programming smart cards, which is nasty sometimes. And the client didn't know really what they wanted, so after some like tweaking the code quickly, because it's F#, so I can implement your new thing quickly and then send it to you, and it's not quite the right thing. And then they weren't friends. I went there, landed in, just as a story to close this, it's another DSL, but I landed in Paris in the morning, went to my hotel room, was like, okay, this is going to be a mess. So I just wrote basically a declarative framework for like how all the questions that we'd had in mind, that we'd had over the phone and couldn't like, I just put all of those as the concepts in there and wrote something that would implement it with wherever the smart card protocol was. And then we just sat down. I literally sat down with the domain expert with this and was like, okay, what do you want? And then we tried it out and it was like, oh no, you're right, that's not exactly what I want. But we were able to communicate at exactly the right level of abstraction. That guy was really confused because it was like, what is this thing? Like, what is this language that you're using? I basically had mapped the thing to XML to not have to recompile as I was talking with him. But he was like, I didn't know you could do this with XML. It's like, it's just a tree. Like you can code whatever you want with this. And that, like, it took half a day. So that was after a few weeks of transatlantic, very frustrated, very frustrated phone, like, because then they would try things, but then I had the expert like sitting right next to me with his thing independently written, and then we just worked through it. We're at the same level of discourse, basically. We're talking about the same things. I wasn't trying to map back his stuff into like F#, even directly, because even that, there was a big transfer there. So That was probably the first one that made it, in this case, like that was the first thing that came to mind, was like, okay, this is not the right level. I might need to separate those two things. So that's it. So I'm willing to talk about this for as long or as not long as you guys want. This was a bit all over the place. I wanted to cover, like, there's a few different, I think, interesting aspects of this, but any questions you have, or like hurling tomatoes is also fine. And I think, things that are uncertain. So I think building this using a computation expression would probably have made sense, and might still make sense as like something to try, to again layer on top as a different way to write it. So that's kind of a to-do item to try it. Basically, I didn't want to add that as complexity on top of what I was doing. So doing it the way I did with distributed unions basically left me focus on like, here's the words, here's the things that are using the words, and here's the thing that implements the words. And like those three were very separate, and I could like focus on them. And then when it worked, I went away to draw boxes and arrows as a good architect.
You might find the computation expression version of this, the errors are just as bad as closure.
And that's another thing, like and I think that's important, like it's very nice to, so I'll close again on something, seems that that's a bit more on the south side, but it's really easy to get seduced by how neatly you can write a snippet.
A snippet.
Right? How pretty it is. But if it takes you 3 times as long to onboard an intern to work on something, or if it takes, which I'm not saying that F# does that, but some things that you can do in F# will definitely do that. Sometimes it can be really clever, but if you need like to teach someone about how type providers work so that they can get some work done, maybe it's not the best fit for type providers. If it's something that they're like, but I could do it this way, and it would work, and if they're right. Like sometimes people say that, but it's just because they haven't like grasped the thing. As I said before, like sometimes you just haven't realized how much pain you've been having from something because it's been there forever. But sometimes people are right. It's like, yes, it's a really clever way to do things. But there are other ways. So that cost has to be taken into consideration. And in this case, I think the reporting, like when, again, tests fail, there's 5 systems involved. Everything's out of orders, the clocks are going out of sync, there's an device in there that loses like 5 seconds every 10 minutes. So it's just like there's so many moving variables at once anyway that the least you want to do is to give better error messages and be like, oh, here's where I was at. Here's what my understanding of the world was, and here's why your test failed, instead of, it's line 1298. You figure it out. And here's some logs of all those systems. So yeah, I think very. So that was actually the last slides. So if you have any questions or comments, we can, if you want to look at some other stuff, we can. I've come all the way from just as warm Montreal right now to do this. So.
Yeah, I've worked with some embedded systems, and I definitely know that one of the things you want to try and do is do that leveraging operation so that you don't have to like sit there and just, chop down a tree with a scalpel. So you're always trying to up level, and it definitely helps a lot.
But the tricky thing is the path backup, which is easily forgotten. Like we've gotten used to debuggers mapping back the instruction pointer to the line of code. Like that's a non-trivial thing.
Right.
You kind of got used to it, but it's not necessarily.
Well, it's because they have the PDB file and it
Yep.
basically marks everything as it does it. So you got to do that.
So that's my to-do list for that, is to build exactly that mechanism so that I can say, look, here's why I was doing this low-level stuff, because it's the same problem. Good job. Yeah.
So seeing that this, you guys went back to, CCR, before, I guess tasks and the
Yes, the
async and.
CCR guy over in Montreal.
Oh,
To
really?
his utter confusion. Like, okay, sure.
But seeing how you guys went back that far, over the years, as you watched all of these other libraries, RX and stuff like that come out, were there any points or anything that you saw from these other systems that gave you a little bit of envy, or did you glean any sort of key insights from any of these other systems, or?
At the library level, not so much. Well, I mean, I say that. I would really like if we could get the performance of the system collection executable into the abstract ones, because they're kind of a bit better. But a lot of engineering has gone into them, so that's perfectly expected. But there's little things like that, like from most of these are solving different problems. So like we have, and we do use, for instance, Aka.net on some of that stuff, which brings some of those things I said we were missing in our implementation. But like some things were always, there were enough things missing that the envy didn't really set in too much. But not really, actually. We've been able to leverage most of the stuff that we had some really envy for. We were able to pull it in.
Any key things that you ended up pulling in? Any ideas you ended up stealing once you saw something else, or?
I've been mostly working at the system level for a little bit now. So like actually coding this was a fun, like, oh, let's get back to, can I still program? And F# is still the loveliest language for me to just like say like, oh, what about this idea? And then just like literally sitting down for 2 hours and being surprised that it works. That was literally my experience. I was like, oh, weird. Not only does my approach work, but the code also worked. So that was nice. But otherwise, really, I've been looking mostly at like composing bigger pieces together, which has completely different feel. Like I am definitely not a believer in like functions all. It's things start behaving a bit differently when you cross system boundaries, and you're like I think maybe you can kind of fake it. Maybe it's worth it. I just don't. I prefer actors in my system, functions within my actors. That's worked best for me in terms of understandability and being natural and not just trying to say, oh. And like I'm trained as a mathematician, so I can see that you can. Like the fact that you can encode it and you can like kind of you can force it in, it works. But I'm also very much aware that the worst thing that mathematicians always do is we leave out so much detail that oftentimes it's important stuff that we throw out the window. The model is good, but like we threw some key stuff out of the window. So that's for some of that stuff. Like I think it's really good if you're building something small, maybe when you're not really crossing a system boundary. So things like that's why I much prefer the Fable approach to the WebSharp approach. Like the isolated things that does like one thing, and I can see putting that in the system. The transparent calls from front end to back end and back, and then it's all some of the parts are compiled into JavaScript, and then they're hosted in web servers. Like to me, that's like, well, okay, but that's a lot of moving pieces that are all dependent on the same block, which makes sense for many applications. But I wouldn't build our big stuff on top of this. So we've built some smaller things with it, and they work really well, and they have some kick-ass libraries. Like it's like that work is great, but when it comes to like making technology decisions for like at bigger scales, I prefer. That's really not answering your question. I'm sorry.
No, it's a good diversion. I mean, now I was gonna follow it up with, as you went through some of the different versions, you guys actually went away from a version that was more purely functional. Did you find that that a lot of the developers struggled with interpreting everything in this sort of like a more pure functional model? I mean, were there certain things that they just struggled to intuit?
It wasn't too bad. So they definitely had to deal with the, the slight disconnect, which I guess comes back to what I was saying. But there's a slight disconnect where like they were writing like, oh yes, it's more declarative, but I remember having the same conversation like 8 years ago, being like, well, maybe like doing a for loop with an index and a collection and then comparing and then doing a break and then comparing the index to the last bound is maybe not the thing that you're trying to do. Maybe you're just trying to see if something is in the list. And I remember having that discussion with C# developers. That was before most of the link queue stuff became popular. And they were like, no, that's what I want to do. I want to, like, what I'm thinking about is moving that index forward. And they, like, it took some time for people to get used to the fact that, oh no, being more declarative in that kind of space, it became natural. And most of the C# code that I see right now, it's very rare that I see some like really imperative stuff in C#. In modern C#, it's usually like kind of a nice mix. The language itself has some stuff, but it's not, modern C# is not that bad anymore is what I'm saying. And how people got used to using those new things. So it was kind of that same switch where they were working from something that wasn't terrible, but it was not all that declarative either. So they had to kind of accept that, okay, I don't know what's going on exactly. Just the same way that the C# people were saying, well, like, how is it looking for something in my collection? How do I know like what index it's looking at? But it took them some time to realize that they didn't actually care. It didn't actually matter to what they were trying to do. And it was kind of the same thing for this. So at first they were like, well, I'm used to doing it this way. Like, how will I, like, I'm used to just having done a try find on my list and then to match on that event. How will I do this now? And it took some adaptation to realize that the stuff that they were losing, it wasn't actually what they were being paid to do. Like, it wasn't really what the task at hand was about. But it didn't take too long. Like, it took a few weeks for them to like start really, because they start mostly by. So the guy that I ended up the project to wrote a whole bunch of tests using it, because that's why I ended up to him, is because he would be using it. So I was like, okay, take it, and then like figure out all the bug and the stuff that I've done, and then extend it if you need to, and then, so that gave like a set of examples of that language, and then he slowly helped other people in other teams basically convert their previous tests to it, which led to other like expansion of the semantics and stuff, because that it's only when you try to do more of it you realize that there's some things that were maybe, again, expressible in the purest sense of the term, but like they were ugly. Like they weren't nicer than what was there before. So we added some of the words to just make it seem more natural. But that was, I would say, a matter of a couple of, again, a few more weeks that those people would, and those were fairly junior programmers. Like they learned F# over the past maybe 6 months. They got used to that code base, and then we just threw them that wild card. Here now, you're going to write this other language that's into C#, into F#. I'm sorry, but they could still leverage a lot of the F# parts, so it wasn't entirely foreign. So I think that helped. So they still had the list, and they still knew out again, like, and they could see some of the value they saw was some of the easier composing, as I said, like being able to just like have a module with just lists of things, lists of basically sentences in that language, and be able to just yield back in there, and then know exactly what that's doing. And then there's no interference between other things, because it's a self-containing like piece of the test. So that they liked at first, and then of course there were, again, when there's bugs in the implementation, it leads to some odd things. But so that kind of answer your question.
Yeah, you did. But kind of piggybacking on that, you're talking about onboarding. It seems like a lot of the younger developers that you're bringing in. I noticed on your website you have a number of internships for where you specify F# as. I mean, is this something that you see coming out of schools? Are they wanting more of functional type of exposure? Or?
It depends on the school.
Okay.
We have, so McGill and Montreal have switched. Basically, their FP curriculum used to be in standard ML, and they've switched to, I think, due to the very intense lobbying of one of our first interns. He doesn't work with us anymore, but he was really good. And he studied there, and I think he lobbied very hard that the school should stop using SML and just use F# instead as something more pragmatic. And they did. And then, like, so slowly we see more people that have that have the interest. And I think it's easier to get the interest when you're learning it. And some other school, they do Lisp, and I love Lisp. Like, I have no problem with Lisps. But if to you, functional programming is just a Lisp, it's like, how does that connect with the rest of my stuff? Like, it feels like, it will feel like something crazy just because you can't interrupt. So I think having F# as that is a good way to make people think of it as, oh, maybe I can use this. Maybe I can actually use this, which is what we need for an intern. Like, an intern is not a big commitment for an intern to do an internship in F#. It's just like, well, if I don't like it, it's 4 months. Like, it's not a big commitment as like an experienced programmer saying, okay, I'm going to learn F#, then I'm going to switch job to do F# full time. Like, that's a big, for someone who has a good control of his tools and is like productive, that's a big call to do. So for interns, that's what we're seeing, and we always have, I guess, probably 3 internships that we don't always fill. I mean, each semester we have a huge. I mean, I started there as an intern in computer vision a few years back, and so we always have, I think, it's something like 70 or 80 interns at any one time. It's a lot of interns.
Wow.
It's really part of like how we build. So our main video surveillance product was initially built by an intern, and our main access control product was initially built by an intern in F#. So we have, that's kind of part of our DNA of doing things that way. So we always have 2 or 3 4-month internship, well, 4 or 8 months internship postings that we have open. We're seeing a bit more. Yeah, we've got some really good people from there.
Any other questions?